Okay, we have so far analyzed induction machines with unbalanced supplies and also single phase induction motors. Single phase induction motor we know is a particular case of an unbalance or asymmetry, right. Now, we can extend the same theory to any type of asymmetry in the stator. Okay. That means, we look at a generalized model, right. Now, we were so far constrained that the two windings were at 90 degrees, right, or 3 windings were at 120 degrees. So, why not we take a general asymmetry where the windings may not be same, okay, they will have different number of turns, and number 2 is they may not be dispossessed by 2 pi by n, right. So, they are not at 120 degrees or 90 degrees as the number of phases. Now, that is one important feature. So, if we can have a theory which can tackle any type of asymmetry, then what will happen is any symmetrical machine will become then a particular case of that asymmetrical model. Is it okay? So, you and then we will try to see whether whatever we have studied under a symmetrical situation, we can get at the same thing. Now, for unbalanced situations, till now you are mostly confined to the so called symmetrical component concepts, but for symmetrical components invariably you require the machine to be symmetrical, right. Your Z1, Z2, Z naught have to be specific, and they were specific to a symmetrical machine. Z1, Z2, Z0 were not for asymmetrical machine, and we somehow correlated what is the correlation between the symmetrical components and the associated fields. We said that the forward field is associated with positive sequence and the backward field is associated with negative sequence, right. And now, if we can look at it a different way, that whenever you have a winding which is excited by a sinusoidal current, we know it give rise to forward and backward fields, is not it, MM. Now, that field will interact with other windings in the machine, both in the stator and rotor, and it is this reaction which will be cumulatively can be studied, right. Now, this is called as generalized rotating field theory. Generalized because it takes care of any general machine, and it is based on the concept of counter rotating fields, because any winding will give rise to in the air gap forward and backward fields, right. So, and that will have a correlation with symmetrical components, but let us see when they are correlated, when they are not correlated, and what is the similarities and differences. Okay. Now, this is what we will try to discuss today. Okay. Now, a performance of an induction motor, you have one there are two aspects of the things. Okay. One is you define it by two sets of equation, one you call it as internal equations, that is internal to the machine, you have an internal equation, and other is external equations, that means how you connect externally. For a machine, what do you connect externally? Electrically you connect a voltage sources, you connect voltage sources externally, and you can connect them also in any asymmetrical fashion. Okay. Just to give an example, simplest way of asymmetry may be, you normally connect this is what you connect, in a way you might make a star connection So, this is one way of connecting, right. Now, you can make you simply you can make an asymmetry. Okay. Now, for some reason you connect them this all right, but you know, supposing you connect like this, so it automatically becomes asymmetrical. You reverse one of the phases by mistake or whatever it is, it may happen, okay, right. So, even in a 3 phase supply there could be, you can create asymmetries either in star or delta. Okay. This is symmetrical, this is asymmetrical, is it okay? But then how do you analyze such machines, right? Then your external equations will become different, because you have only voltage sources V A, V B, V C, is not it? How this V A, V B, V C get connected to the winding, the voltage sources, okay? So, the sources and the machine. So, this connection is external to the machine. From the terminal to this you have external equations, but when you go into the machine there is internal equations. Okay. So, this is one thing we generally do this. Okay. And what are the internal equations? That is internal to the machine, they are peculiar to the machine, and you express the phase voltages in terms of phase currents and the parameters. Okay. So, internal to the machine your phase voltages and phase currents, and can you make some type of parameter. That means, can I write in some form, you know, let us say if you say V A, V B, V C, I can write a matrix or impedances I A, I B, I C. So, can I define a Z matrix, right? You know each, so that is internal behavior. So, you can always say, I can always say Z A, Z A B, Z A C, because we are all looking at sinusoidal steady state. So, with all impedances, not transients or dynamic. Okay. So, this will be Z B A, Z B B, Z B C and Z C A, Z C B, Z C C. So, we supposing if it is a 3 phase machine it will be this, but if it is M phase machine you can have similarly M into M matrix, M currents and M voltages, right. So, let us say can we evolve into this, right. Now, so therefore, these are called the what Z inside, what should it be? These are called also rotating field parameters. Okay. Now, these are based on generalization of counter rotating field theory. And now, another thing is we should include space harmonics. What is space harmonics? What is space harmonics? We have been always talking about harmonics, right. I always say here we talk two things, one is space harmonics and time harmonics. What is space harmonics? Due to? No, it can happen in symmetry also. No, non-uniform air gap may create, but what is space harmonic? See, harmonics in MMF wave, right. See, you have an MMF, supposing you have a conductor, a coil which is placed like this, A dash, A dash, okay. You know that if you have just a one conductor, the MMF waveform may be squarish like this or rectangular, okay. Because flux lines will go up like this, is not it? because this will be the flux line, is not it. If you pass a current, the flux will go round. So, if you place inside a slot a coil, one coil, so in effect it will not be a sinusoid, it will be a rectangular one. Okay. And now, if you make more coils, supposing I have instead of one I have, let us say 3 coils, something like this, then you know that it will give rise to some type of a stepped wave. Okay. So, it will it may have it may go like this. Okay. Right. So, it will be a stepped wave if you have a more coils. So, one coil it is like a superposing rectangles, but displaced by the slot angle, right. So, you have one rectangle, maybe another rectangle, like this. So, add it, you will have a cumulative stepped wave. Is it clear? Now, but in all our analysis, what we do, we always say, okay, I mean maybe like that, but I only take the fundamental. This is the fundamental F1. We take fundamental only, because we do not take the harmonics, right. But any non-sinusoidal periodic wave will automatically will have harmonics, right. So, it will have third harmonic, fifth harmonic, seventh harmonic, because if it is asymmetry is there, it may even give a rise to even harmonics. So, this may have a third harmonic. So, this may be F3, right, and maybe it can even have fifth harmonic. Okay, 1, 2, 3, 4. So, this may be F5. So, in effect your MMF will have F1 plus F3 plus F5, etc. Okay. And it can, in general, even you can have the MMF will be sigma Fn n equal to 1 to infinity, is not it. So, you can say, let us say F1 cos theta plus F3 cos 3 theta, etc., or maybe even it can have F2 cos 2 theta also. So, it can be a sigma Fn cos n theta n equal to 1 to infinity, is it right. So, I am just writing the standard Fourier series. So, these are all apart from fundamental, you call these as space harmonics. Is it clear? Any doubt? Okay. All of you are clear now. What do I mean by space harmonic? So, any non-sinusoidal wave, MMF wave produced, okay, it will give rise to this, right. Now, what will be its impact? What will happen in the so called rotating field concept now? I apply, for the machine, agreed, that there are, you have a a machine and which will have all the harmonics, right. So, it will have the fundamental, okay, and it will have the third harmonic, MMF wave, okay, etc. But you pass a current I in the windings and you call it as I equal to I max cos omega t, sinusoidal volt current you are passing. Now, then we told that it will give rise to forward and backward fields, right. So, this let us say F1 will lead to F1 forward plus F1 backward, is not it? Is right? It will give rise to with half the amplitude, okay. It will one moving forward, okay, and another moving backward. Sorry, with half the amplitude. Agreed. So, that is what we said. If it is only the fundamental is assumed, but what about third harmonic? Because this third harmonic, this will also give rise to third harmonic forward plus third harmonic backward, is not it? Okay. Now, what is the difference between the fundamental and third harmonic? What speed and what pole number? So, if this has pole number p, this will be 3p, okay. And what will be the speed of the field? So, this corresponds to ns, this corresponds to ns by 3. So, what will be the frequency of induced voltages by these fields? Will be Fs by 3? What will be the speed? You know, after all, you told it will running at, say, if fundamental is 3000 rpm, this will be 1000 rpm, is not it? And the fundamental is 2 pole, this will be 6 pole. What will be the frequency of induced voltage by these fields in the same winding? After all, these fields will also induce, there is induced voltage in the winding. What is the frequency?
It is forward n plus 1 minus s by n.
So for ns it will be this will be s times of fs, and for
No, there is no s here. There is no s slip at all. Do not bother about slip. See, it is winding is sitting pretty stationary. It is you are passing current, okay, and it gives rise to a field in the air gap, okay, and those fields, these air gap fields will induce voltages in those in winding, including the one which is carrying the current. It will be F only. So, frequency, important thing is frequency of induced voltages by all space harmonics will be same, and that is same as F, the fundamental frequency in which you are exciting the winding, okay. But if you want to make things complicated, if the current going into the winding has time harmonics, the current is not sinusoidal. Nowadays with power electronics you make everything very messy anyway, right. So, current carried will also have, instead of 50 hertz, 100 hertz, 150 hertz or whatever it is, okay. So, then what will happen? It will also induce those additional frequencies, because you will have additional fields. Even with sinusoidal current, even with sinusoidal MMF, you will have 3f, 5f and so on. Okay. So, that is time harmonics, right. Any doubt on this or any confusion? Have you understood? There are two ways. One is the winding will give rise to a non-sinusoidal MMF distribution in the air gap, which give rise to additional fields other than the fundamental field. Another thing is you do not pass 50 hertz or the fundamental frequency current into the windings, but you can also give a non-sinusoidal current fed into the windings, which will add to additional currents and additional fields. Okay. So, you will have NF induced because of nth time harmonic. Okay. Now this any doubts?
Sir, this time harmonics again will produce space harmonic.
Time harmonic will produce space harmonic. Time harmonic will not produce space harmonic. Time harmonic will produce time harmonic. Okay. But it will give you additional fields, right. So, the thing is you can say, for example, say if you only put f, it will give rise to different fields, that is n, let us say 3n, 5n, okay, which will be having p, sorry, n by 3, n by 5, this will be 3p, 5p etc. Okay. Now, if this in addition if you have, for example, let us say 3f, okay. So, 3f will results in what? Synchronous speed will become 3n, okay, and then this will be n, 3n by 5, right, and then again the poles will be same, okay, p, 3p, 5p etc., and this will all give rise to 3f now, whereas this will give rise to f, right. So, but then your fields are different. Okay. Now, we will go back external equations. These are peculiar to the connection and express relation between the phase voltage and currents, supply voltage and impedances. Okay. This is external to the thing. Suppose you connect a capacitor, it becomes external equation. Okay. Therefore, sometimes they call it as inspection equations, and by so you write the external equation by just simply writing Kirchhoff's laws. Okay. External is KCL you write, there is no problem. Okay. Now, we have seen it, I think it is just a repeat. So, a single phase induction motor, main and auxiliary windings, supposing they are not displaced by 90 or 120 degrees. See, it happens, supposing this is again a peculiar case where it is not 90 degrees or 120 degrees. Okay. Then also you are concerned with space harmonics, okay, because electrical asymmetries are there. Because electrical asymmetry, there will be space harmonics. Okay. Now, this generalized rotating field theory, what we are now going to discuss is extension of the counter rotating field theory, which includes space harmonics. So, what we are trying to say is there will be forward fields, there will be backward fields by fundamental and also by harmonics. Okay. So, if you have single winding excited by AC, so you will have a series of chain of fields in the air gap. So, you can imagine it is like several magnets rotating after several pole strengths or several fields, several speeds. Okay. So, it is not such a disciplined situation, pretty indisciplined, just like your hostel mess or something. Okay. So, so many people like that. Okay. So, now involves solving. So, we have to think of a internal and external equations. Okay. So, let us see how we go about it, right. Now, on single phase machine we have done, I do not want to repeat it further. We have already seen if it is only one winding is there, then you take the other two windings carry in a inspection equation. In that case will be you have only one winding carrying a voltage V across A phase and B phase do not carry the current. So, we have already seen that this results in the 3 currents I naught equal to I 1 equal to I 2 equal to V over Z naught plus Z 1 plus Z 2. Okay. And we have also seen that the current in each phase will be 3 V over Z naught plus Z 1 plus Z 2, that we have done. Okay. We have done using the symmetrical component concept. Okay. So, impedance in a so we are expressing the impedance in terms of the sequence impedances, saying Z naught plus Z 1 plus Z 2 by 3 is for a single machine. So, if you have one winding, we write it in terms of 3 impedances. Okay. You apply a voltage V, it draws a current I decided by Z 1, Z 2, Z naught all by 3. This we have done this. Okay. Now, if you have a 2 phase model, okay, where only one phase is excited, then we say I B equal to 0 and V equal to V A. Okay. Then again we did the same thing, let us say 2 phase V minus V A dash and I B dash is 0, and we got the expression I 1 dash equal to I 2 dash equal to V over Z 1 dash by Z 2 dash. This we have done this, and I A dash, that is the current in the A phase, will be equal to I 1 dash plus I 2 dash, which is 2 V over Z 1 dash plus Z 2 dash, that we have done. Okay. So, the impedance here will be Z 1 dash plus Z 2 dash by 2, and so if this is the V A and this is the I A, or dash is only to indicate that they are a 2 phase system, then we have done this Z 1 by Z 1 dash by 2 and Z 2 dash by 2, and we discovered Z 1 Z 2s are different in a 3 phase mode and a 2 phase mode. Okay. And we proved that both are effectively the same impedance, right. Now, the question is what will happen with the space harmonic being present. Okay. Now, in many of the machines the third harmonic is predominant. Now, the third zero sequence component will have predominant third harmonic. If it is 3 phase machine, zero sequence will have third harmonic, but 2 phase machine, if you have 2 phase symmetrical components, now that third harmonic, see if the third harmonic is there, it has to get into one of these impedances Z 1 or Z 2. Okay. So, this third harmonic, which can be accounted for in a 3 phase model, cannot be accounted in a 2 phase model, and so third harmonic has to somehow get into the Z 1 or, because there is no Z naught here. Okay. Now, how this has to be accommodated, that is what we will see today, right. If the 0 sequence is associated with third harmonic air gap fields, if it is a 3 phase model, it is okay, but if you have 2 phase model, what happened to that? Okay. Okay, now what we need to understand is, in the generalized rotating field theory, analysis of pure single phase motor by counter rotating field theory, then we look at the general polyphase machine, and we look at the symmetrical 3 phase machine, then we look at the symmetrical 2 phase machine, and we look at a general case. These are the things we will now look at. First, let us take only one winding excited, write the equations, add other windings, write the general equations, then particular cases we will see and see where we are leading to. Okay. So, we are getting into a tunnel, okay, and then we will see how to come out of the tunnel. Okay. Now, we are saying that MMF produced by a single phase winding supplied with sinusoidal current, no time harmonics, is stationary in space. This is a statement and this you know, and pulsating at a frequency at supply frequency. This is what you know. So, it is a magnet which is goes on pulsating, but axis is not changing. It is a standing wave, goes on changing, sometimes becomes north pole, sometimes south pole. It has a different magnitude in between. Okay, sometimes 0 poles, I mean 0 magnetism. Okay. So, you know it is a pulsating field. Now, we have said this MMF wave can be resolved into 2 rotating wave. Therefore, we have infinite series of harmonics now, right. That is what we have mentioned already. We have infinite series of harmonics rotating, but axis is same of one winding axis, right. Is it clear? So, we have several fields. Now, if the single phase winding is symmetrical, okay, then only odd harmonics are present, but means you know if the phase belt is 180 degrees phase belt symmetrical, but if you make it asymmetrical, you know, then even the harmonics may be present. Okay. Supposing you know if you have a nice MMF wave like this 0, pi, 2 pi, it is symmetrical. But supposing you do not make it 180 degrees, you make it 160 degrees for some reason. So, if supposing your waveform is see if your waveform is like this 0, it may not be pi, pi is here and this is 2 pi. Supposing I put the coil here like short carding, I am just give you one example. Then this F1 and this is F2 which is not same, here F1 equal to F2 symmetrical. Here there will be what you compare these two waveform, what harmonics will be present, what harmonic will not be present. Here what will happen in this top? No even harmonics. Here there will be, it will have both odd and even. Here only odd. So, 1, 3, 5 will be there because of symmetry. Okay. So, a general practice we can consider both odd and even harmonic fields. Let us consider this. Okay. Now, we also know the stationary pulsating field is resolved into 2 equal opposite fields having magnitude half of the original field. I mean this is MMF resolution, not the field resolution, not the flux. We have explained it coincidentally. Okay. So, same principle can be applied to each of the harmonics of the MMF wave. Okay. So, each harmonic component, each harmonic means there is one forward field, one backward field of stator MMF. What will it do? It give rise to induction motor reaction. There is one forward field. In fact, you are happy in 3 phase symmetrical machine because there is only one field to deal with in the air gap. Then we make single phase, we had one more field which was going the opposite direction, okay, backward field. Now, I am introducing more fields, okay, only with one winding only. So, but they will, each of the field will react with the rotor. Rotor we are taking squirrel cage only. Rotor we are, fortunately we have not done anything with the rotor. Okay. Rotor is a squirrel cage short circuited rotor. Each of the field will induce currents in that. No, they are impartial. So, each of the air gap stator MMF will induce a current into the rotor. They will react, it will produce its own flux, MMF excitation and its own forward flux. Okay. Now, at standstill both exert equal and opposite reactions. If the rotor is held at standstill, reaction is expected to be same in the rotor conductors, is not it. If the forward field passes at any instant in any bar some x ampere of current, the backward field will also produce in the same bar x ampere of current, right, at that instant, right. Therefore, but on the rotor, and thus rotor cannot distinguish between forward and backward field at stationary when it is stationary. Okay. When stationary, relative speed is same. Okay. But when it is running condition, reaction is different. Forward field will induce a different current and backward field will induce a different current, because relative motion of the rotor conductor with respect to the respective fields is different, right. So, they will all be, so forward backward reaction will be different. So, each of the flux waves, okay, therefore, there will be one forward flux resultant flux wave, one backward flux resultant flux wave, each of them will induce a voltage in the same stator winding, okay, same stator winding. So, each of the field will induce a voltage. Okay. After all, this stator winding is sitting pretty in the stator slots, but it will go on be touching several fields, which are also, this field is also will have an impact of the rotor currents. Okay. Is it okay? Therefore, this will be both forward and backward field will be there, right. Now, what will be the voltage that will be in the winding? Okay. So, if this is the winding in which you want to know and you are applying a voltage V, is not it? Applying a voltage V and passing a current I. What will be the voltage? There will be voltage due to the leakage reactance drop, is not it, in the winding. There will be voltage due to the fundamental forward field, there will be voltage due to the fundamental backward field induced in the same winding, okay, is equal to 4.4 Fn phi, right. There will be voltage due to second harmonic forward field and second harmonic backward field, right. So, you can have any voltages, all will be there induced in the same winding. Is it clear? Well, one due to its own winding resistance leakage reactance, and then this will all be inducing the voltage all at fundamental frequency, right. Therefore, we can write that voltage induced will be VL, that is due to leakage reactance, voltage induced in the winding due to its own resistance and leakage reactance. Okay. Then it will be a voltage due to all forward fields n equal to 1 to infinity, and voltage due to all backward fields n equal to 1 to infinity. Okay. Are you clear with this step? Okay. Now, we will consider the voltage induced due to forward field by the current I can be represented by I into ZFN, that means Vf n will be I into ZFN and Vbn will be I into Zbn. Okay. So, this ZFN is the net forward impedance, okay, and this is Zbn is the net backward impedance, which includes the rotor reactions, which includes the rotor resistance, leakage reactance, everything, you know, Zf, Zb. Okay. If you neglect the harmonics, this will be only Zf1 and Zb1. Okay. So, we take all harmonics into account. So, there is a voltage which will have each of the fields will give rise to this. Okay. So, we can now say a single winding excited by current with applied voltage V, a phase current I will have a ZL will be resistance and coil end reactions. So, it will not include the leakage reactance due to harmonic fields that may go into Z its own air gap fields. ZFN is called the impedance corresponding to nth harmonic forward field, ZBN impedance corresponding to nth harmonic backward field. Okay? ZFN, ZBN. I want you to understand each step which I am taking, do not skip. If you do not understand, please stop me, right?
Sir,
Yes.
we are considering V as a stator voltage,
Applied voltage.
applied voltage.
Yes.
Then sir, it will rotor currents will have some effect on that also, no? Because rotor current will induce some voltage.
Yeah, no, that is why rotor current will induce rotor currents. What will it do? If a current is induced in the rotor, it will produce an MMF in the rotor surface, isn't it? And the forward flux will be changed because of rotor currents. Forward flux is how is the voltage induced? Voltage is induced not due to MMF, it is due to flux. Which flux? What is the net air gap flux? So, already rotor current will have an impact on the voltage induced, because that will have an impact on the net air gap flux. When there is a rotor current there, rotor surface get magnetized differently in proportional to the rotor current. Okay. So, what is the net flux? See, air gap flux is due to the MMF between the stator and rotor surface, right. So, rotor reaction is inbuilt in these impedances, okay, it is already there. In fact, if you want to know what is the impedance, in fact, it is given in the literature. So, in fact, even the ZFN will include some leakage path as well as it will have some impedance, it will also have some RC, the core loss component, this XMN by 2. So, this will be RR by SN and this will be XRN or something like that. Okay. So, it is already there, right. So, this current which will be going here will have an impact on this. So, this is your Z, because this is your VFN across the nth harmonic, same with VBN. Okay. Right. So, single phase induction mode, the equivalent circuit will contain all harmonic impedances in series with fundamental impedance. Okay. Now, the effect of stray losses is neglected to avoid complexity, because there are also stray losses. Each of the field will also induce create some eddy currents in the cores. So, that will also create, and each of the fields will also create some leakage fluxes, etc. Okay. So, that is how induction machine, though it is simple to make, is complicated and it and creates all these problems, okay, in analysis. Yeah. Now, we will represent the equivalent circuit of a single winding machine like this. This is V and this is I. This is the ZL leakage impedance. This is typically RS plus JXL S. So, ZF1, ZB1 and up to ZFN, ZBN, is not it? So, it will each of this. So, this will be VF1, VB1, VFN, VBN. These are the voltages induced in the same winding. Okay. Right. Now, this is for one winding. Okay. Now, you can have a general machine with 3 windings, say. This is your reference winding. A winding we take as a reference. Now, this B winding we may be at some angle theta b with reference to A, and the C will have another angle theta c with reference to A, is not it? Need not be 120 degrees. I am making a general case of this, and this may have, let us say, KB times the A winding, and this may have Kc times the A winding, right. Number of turns may be in a symmetrical machine, theta b equal to theta c, there will be 240 and 120 degrees respectively, and Kb Kc will be 1, right, that is symmetry. Okay. Now, we take a 3 phase machine and rotor is symmetrical. Now, if A phase as a reference, we will take a general equation, just write the general equation, stop it. Okay. Now, we have said turns, ratio of turns on BC is Kb Kc, but for nth harmonic it may not be same because there is a winding factor. I hope all of you know winding factor, is not it? Winding factor will depend upon the harmonics, right. So, there will be Kbn Kcn, okay, due to the winding factors. So, in general case what we can write it is Va, Vb, Vc will be like this impedances, okay. We can write it in this fashion in terms of Ia, Ib, Ic. Okay, now what are these impedances? Za is what? Za we have written already, that is what is Za is V by Ia when Ib, Ic is 0, okay, Za, right. Then that is okay, ZAL, ZFN, ZBN, that is what we have written, okay. Now, what will be the what is ZAB? ZAB is the voltage induced the B winding due to A phase current, is not it? It is ZAB represents the voltage induced in the B winding due to A phase current, okay. Then what will happen? Since the B winding is having Kb times the A winding, right, number of turns. So, Kb will be there, then the voltage induced will be, of course, that will also have the nth harmonic Kbn into Zf, whatever, if it was inducing a voltage Zfn in the A winding, it will induce a voltage Kb, Kbn times Zfn into, and when will it induce? It will induce after theta b, because it is located theta b angle with reference to A winding, okay. So, forward field it will be e to the power of minus j n theta b, okay, and backward field will be e to the power of plus j n theta b, okay. See, forward backward field it will induce, as we have discussed in 2 phase machines. So, there is a voltage induced in the B winding due to A phase currents. If it was producing a voltage V in the A winding, it will produce a Kb times V in the B winding, but it will not induce in the same phase. There is a phase shift given by e to the power of j n theta b, and one will have minus theta b and another will have plus theta b because of directions, okay. See, so you can write the same thing, Zs you can write, this will become minus theta c, okay, this will plus theta c, and Zba will become, what will be Zba? It is almost like a transpose of where there are complex numbers. So, this will be, do not you think this will be ZAB transpose, huh? Is not it? So, that is the voltage induced in the other way around, okay. Kb times this into e to the power of, if you minus theta it will become plus theta b like this, okay, and Zca will be whatever Zac whatever happens, but if it is minus theta c it will become plus theta c. Is it clear? Okay. So, we can write the impedances, all these impedances. So, you can write down the whole impedance matrix, is not it. So, you can write ZBB, ZBC, ZCB, ZCC. Similarly, okay, because ZBC will be product of KBKC, right. So, this way and nth harmony you can write this. So, I suggest you try to introspect these impedances before we try to take it further. Is it clear? So, we write the impedance, these are called rotating field, general rotating field impedances. Okay. So, we will stop it here and take it further next class. Okay.